Hello friends, today in this session we will discuss car following models. This car following model describes how one vehicle follows another vehicle in a lane under uninterrupted flow condition. And there are several forms of car following models to represent how a driver reacts to the changes in the relative position of the vehicle ahead. Models like Pipes model, Forbes model, General Motors model are very important and generally used. But before I tell you about these models, let me just explain the concept of car following. Now, let us consider a case of vehicles following each other on a road stretch of highway, and let's assume that the flow is uninterrupted. So there are two vehicles in the lane, vehicle number 1 which is a lead vehicle and vehicle number 2 which is a following vehicle, and the distance between these two vehicles is s. Now this S should be such that if the leader applies a sudden deceleration, the following vehicle has sufficient time and distance to perceive this action of the leader, react to it, and be able to decelerate without colliding the leader. And let us assume that at this point of time, the leader decides to decelerate and stop. So it will take some time to react to the action of this leader. And after that, the following vehicle will also apply brakes. So the position is like this, that this vehicle 1, that is leader, decides to decelerate and it comes to stop position here. And this vehicle will take some time to react and then apply the brake. So there are two distances. One is x naught, when this vehicle follows the leader and stops here. Now this is the minimum distance which is required, and that is called the safety margin. And let us say L is the length of the vehicle. So the distance required by the first vehicle, that is leader, to decelerate and stop will be XL V square upon 2 DL. DL here is the rate of deceleration of the lead vehicle. And the following vehicle will require certain reaction distance, that is V into T, plus the braking distance V square upon 2 DF. DF here is the deceleration rate of the following vehicle. And you can say that the total distance required by this vehicle, the following vehicle, will be Vt plus V square upon 2df. Now this distance xf you can write as s is here, s plus xl, that is the distance required by the lead vehicle to stop, minus length of the vehicle minus x naught. Or if you rearrange these, then you can write down that S is equal to V into T plus V square upon 2 df minus V square upon 2 dl plus x0 plus L. This is the basis of car following theory, this equation. For given parameter, it is possible to compute the necessary spacing so that the following vehicle will just be able to avoid a collision by anticipating the action of the lead vehicle. And if you consider the values of DL and DF, three particular values of deceleration are relevant to safety. Dn is, let us say, normal or comfortable rate of deceleration. De, emergency rate of deceleration. And infinite, when you have instantaneous or stone wall stop. For example, in case of accident, the vehicle comes to stop immediately. So acceleration or deceleration rate becomes infinite. So depending upon the value of df and dl, there are 5 regimes of flow, A, B, C, D, E. When DL is infinite and DF is normal rate of deceleration, that is regime A. Similarly, when DL is emergency rate of deceleration and DF is still normal, then it is B. And C is when it is infinite and it is emergency, and D is when DL and FDF are both same, and E is when there is no braking required. That means both are moving at the same speed. And if you plot these for some values of parameters, you will find that the distance s changes with speed for different regimes like this. So if you have high rate of deceleration of lead vehicle, you will require more safety distance between the two vehicles. So this equation is fundamental to car following, and I'll explain how this equation can be used even to determine the capacity of the road. Let us put some values here. So let us assume that dl is 2.5 meter per second square, df is 2 meter per second square, length of the vehicle is 6 meters, safety margin is 1 meter, reaction time is 1 second. So with these parameters, if you put these values in this equation, you get s is equal to v plus v square upon 20 plus 7. Now you can make a plot between v and s. Remember, v is in meter per second and s is in meter. So with this equation s, you can find out the k. K is inverse of spacing. So you know that this relationship q is equal to k into v. So q is v into k. K is 1 upon s. So you can find out what is the flow with the different speeds, and you get this kind of curve. So you can see that the flow is maximum at a speed of around 12 meter per second, and this flow is 1648 vehicle per hour, and that is the capacity of the road. This capacity of the road is for these parameters. If you change the parameter, the capacity will change. Now with this background of car following, let us now discuss different types of car following models. But before that, we should understand the notations which are universally used in car following models. Now there are two vehicles. One is the lead vehicle, which is n vehicle, nth vehicle, and another is follower vehicle, which is n plus 1th vehicle. Length of the vehicle is L, and distance between these two vehicles is D, or you can say X. Now notations which are used here: for lead vehicle we take suffix n, x is the position of the vehicle, x dot is the speed of the lead vehicle, small t here time t, and t plus delta t is delta t time after t. Similarly for following vehicle, this is n plus 1th vehicle, and therefore length of the following vehicle is L n plus 1, position x n plus 1, speed x dot n plus 1, acceleration x double dot n plus 1. So with these, the first model which is given by pipe is called Pipe's model, and this model says that following vehicle will keep a safe distance from the lead vehicle, and that is equal to 1 car length for every 10 miles per hour of speed it is traveling at. So distance, minimum distance between the lead vehicle and the following vehicle, that is the position of lead vehicle and position of following vehicle at time t, is given by length of the vehicle Ln plus the speed divided by 10 miles per hour, and this factor is to convert miles per hour into feet per second, because this speed is in feet per second multiplied by the length of the vehicle. So that is the Pipe's model. So if you take length of the vehicle 20 feet, then minimum distance will be 1.36 into speed of the following vehicle at time t plus 20 feet. So minimum distance here is given by this equation, and you can say that time headway between two vehicles will be 1.36 plus 20 upon speed. So this model basically says that the minimum safe distance increases linearly with speed, and the minimum time headway is 1.36 even at a very high speed. When the speed becomes infinite, then the absolute minimum time headway is 1.36 second. Now the problem with this model is that the results of this does not match with the field results. This is the minimum safe distance which increases linearly with the speed, and these are the data which are obtained from the field. So you can see here that this pipe model deviates at very low speed and very high speed. The second model of car following is Forbes model. And it says that the time gap between vehicle must be greater than the reaction time of the following driver to perceive the need to decelerate and apply the brakes. And therefore, the minimum time headway is reaction time plus the time required for the lead vehicle to traverse a distance equal to its length. So mathematically, you can say that the time headway between two vehicles is the reaction time delta t plus length of the vehicle divided by its speed of the following vehicle. So again, if delta t is taken as 1.5 second, length of the vehicle, if you take, let us say 20 feet, then this will become 1.5 plus 20 upon speed. Now here also the same problem, that it does not match with the field data. Now here you can say that the time headway required according to this Forbes model at lower speed is lower than what is actually measured in field, and same is the case at high speed. But the very versatile models which are used, that is general motor model, and car following theory developed at GM were very much extensive and are of particular importance. The research team developed 5 generations of car following models, and the basic equation is that response is the function of sensitivity and stimuli. The response is always represented by acceleration or deceleration of the following vehicle, and stimuli here is represented by the relative velocity of the lead and following vehicle. So speed difference between the lead vehicle and following vehicle is a stimuli, and to this stimuli the following vehicle will respond by either deceleration or by acceleration. And there is a sensitivity parameter. So first GM model assumed the sensitivity term was constant, that is alpha. So the acceleration at time t is equal to t plus delta t of the following vehicle will be given by the time, the speed difference between the following and leader at time t multiplied by a sensitivity parameter alpha. The sensitivity parameter ranges from 0.17 to 0.74 with the average value of 0.37, and this is a very wide range, and the significant range in the sensitivity value of this model indicated a need for spacing between vehicles be introduced into the sensitivity term, and that is how the second GM model was proposed. So this second model proposed that sensitivity term should have two states, that is when the two vehicles are closer, a high sensitivity value should be employed, while if two vehicles are far apart, a lower sensitivity value can be used. So alpha 1 or alpha 2, equation is same. In place of alpha, now you have alpha 1 or alpha 2. But when this model was proposed, there was no guideline how this alpha 1 or alpha 2 should be chosen. And that resulted in the third GM model, because difficulty in selecting alpha 1 and alpha 2 values and difficulty associated with the discontinuous states motivated investigators to perform further field experiments so that distance headway can be incorporated into the sensitivity term. And therefore, the third model proposed sensitivity term is inversely proportional to the distance headway. That is, alpha is equal to alpha naught upon d, and d is the position difference of leader and following at time t. So this equation now is that acceleration at time t plus delta t is equal to the sensitivity parameter alpha, which is given by this equation, multiplied by difference in the speed of two vehicles. The fourth model is based on the concept that as the speed of traffic stream increases, the driver of the following vehicle will be more sensitive to the relative velocity between the lead and the following vehicle. And the sensitivity parameter which was introduced here as the speed of the following vehicle. So the sensitivity parameter here, remember this is same in all models, that is the difference in speed of following and leader vehicle. The sensitivity parameter here includes speed of the following vehicle at time t plus delta t divided by the difference in position of the two vehicles. But the generalized model is the fifth GM model. This is the generalized approach by introducing a generalized exponents to the speed and distance headway component, and this is the final model which is given by General Motor for car following. That the acceleration at time t plus delta t is given by alpha into speed of the following vehicle power m, and difference in the position of the two vehicles to power L. Now these two exponents L and M. L here is called the distance headway exponent, and it can take value from plus 4 to minus 1. M is a speed exponent, and it can take value from minus 2 to plus 2, and alpha is a sensitivity coefficient. Now these parameters are to be calculated using field data. Now here in this model you can see that when M is 0 and L is 0, it becomes the first and second model. And if when M is 0 and L is 1, then it becomes the third GM model. And when M and L are taken 1, then this becomes the fourth GM model. So this is basically a general model in encompassing all earlier four models and with more accuracy to the field data. I can explain this car following model with the help of one example. And the example is like this, that there are two vehicles, lead vehicle and following vehicle, and they have initial distance headway of 25 feet. The lead vehicle is automatically controlled to accelerate at a constant rate of 3.3 feet per second square until a speed of 44 feet per second is achieved, after which a constant speed of 44 feet per second is maintained for 10 seconds. Following the 10 seconds period of constant speed, the lead vehicle decelerates at a constant rate of 4.6 feet per second square until it is stopped. The driver of following vehicle is to follow the lead vehicle with a safe minimum distance headway, that is 25 feet. The question is to track the trajectory of both vehicles over space and time using car following theory. So there are two tasks here. Task 1 is to track the lead vehicle over space and time. It is done first because the trajectory of this vehicle is predefined, and following vehicle trajectory is based on the lead vehicle trajectory. And for this, we use the following equation, that is speed at any time t plus t is given by the speed at time t plus average of two acceleration at time t and acceleration at time t plus t into time interval t. Now this equation is same as this equation, that is v is equal to u plus at. Now here a is taken average of two accelerations, acceleration at time t and acceleration at time t plus t. And if you want to find out the distance of the vehicle, then it will be given by this equation, x1 t plus t is equal to initial distance plus speed into t plus average of acceleration into t square by 2. And this equation is same as the equation of motion, s is equal to ut plus half at square. Only difference is that here this parameter is also added, that is initial distance. Task 2 is to track the following vehicle over space and time. And for that we use car following theory and equations of motion. And for this example, we take the first GM model with reaction time of 1 second and sensitivity value of 0.5. And this is the equation of first General Motor model. So here task 1 is to calculate acceleration, speed and distance of lead vehicle. Let us take time 0, 1, 2, 3, 4, 5 and so on. Acceleration is 3.3 constant until you get a speed of 44 feet per second, and speed you can calculate here using this equation, that speed at any time t plus t is initial speed at time t plus average of two accelerations into time interval t. Now because this acceleration is constant 3.3, so average will be 3.3. So initially for time t is equal to 0 plus 1, that is here, speed will be 0 into 3.3 into time interval 1 second, that is 3.3. Similarly for next every second the speed will increase by 3.3 feet per second. And if you want to calculate distance here will be given by this equation, that is your original distance, which is 0, plus original speed at time t, that is ut, s is equal to ut. Now speed here is 0 at time t, first time interval, okay, not t plus t, plus rate of acceleration into t square by 2. So this is 0, and this is 3.3 at t plus t, and 0 at t time t, that is 0 time, by 2, that is 1.6. Similarly, you can calculate acceleration at different time interval and speed, and when you see that speed is reached 44 feet per second, and this speed reaches 44 feet per second at 13.33 second. After that, acceleration is 0, speed is constant, and therefore distance will increase at a rate of 44 feet every second. And it will continue. It will continue for next 10 seconds. So up to 23.3 second, this will be speed. And after that you have deceleration rate. So speed will decrease by 4.6 every second, and you will have distance increasing at a constant rate. Now this is the lead vehicle, that is a trajectory of lead vehicle, and it will continue until the vehicle comes to a stop position, that is when the speed becomes 0, and that will happen at time t is equal to 32.89 second, and total distance traveled by this vehicle will be 943.4 feet. Now the task 2 is to track the trajectory of the following vehicle, and that is done using this equation, that acceleration of following vehicle at time t plus delta t is sensitivity parameter into difference in velocity at time t between the following and lead vehicle. So here alpha is 0.5, and delta t you can take either 0.5 second or you can take 1 second, and that is, this table is now added here. This was the table, the first part of table was for lead vehicle, and this is for following vehicle. So let us say you want to take delta t as 1 second interval. Reaction time for following vehicle is 1 second. So for first 1 second, there will be no change. This vehicle will remain in stationary position. After 1 second, after reaction time at t is equal to 2 seconds, this vehicle start accelerating. So at t is equal to 2, that is t plus delta t, 1 plus 1. Okay, this acceleration will be given by alpha, that is 0.5, multiplied by difference in speed of following vehicle and lead vehicle at time t. Now the lead vehicle had a speed of 3.3 feet per second, and following vehicle had a speed of 0 at this point t is equal to 1, and therefore the average, the difference will be 3.3 multiplied by 0.5. So that is the acceleration of this vehicle at time t is equal to 2. And if you want to calculate the speed will be 0.825 using the equation v is equal to u plus at. U is 0, a is average of these two values, that is 0 plus 1.65 by 2 into t. T is 1 second, and therefore this will be 0.825 feet per second. And similarly, you can find out the distance also. Similarly, if you want to find out speed and acceleration at time t is equal to 3 seconds, so here you will take the speed difference at time t is equal to 2. That is the earlier interval. So at time t is equal to, the speed of the lead vehicle is 6.6, speed of the following vehicle 0.825. So 6.6 minus 0.825, into alpha 0.5, that will give you 2.8875, and then you can calculate the speed. So that is how you complete this table for following vehicle. Now once you know time, speed, acceleration and distance, you can plot these on a graph paper. So that is the time and this is the acceleration rate. Now this line, firm line here, shows for the lead vehicle, and these dot points here is the following vehicle, and you can see how it basically lags. And similarly you can plot a time versus speed. Speed increases for lead vehicle from 0 to 44 feet per second, and that happens in time interval of 13 point something, and then it becomes constant speed, and then it decelerates at a rate of 4.6 feet per second square. And this will be followed by the following vehicle by the dot points. Following vehicle has almost a constant increasing speed, but with a lag of about 2 seconds. So friends, thank you very much for watching this video. That is how we use car following model to draw the trajectory of lead vehicle and following vehicle. I hope you liked it. You can write your comments in the comment box.